But if you will recall, at the beginning of the year even, we did equations of motion. And the equations of motion were the ones that you're familiar with. You're familiar with finding your velocity by taking your initial velocity and multiplying it by your acceleration times your time. The second set of equations that we kind of manipulated into, we could say that the distance that it traveled, the change in x there. And so what you'll find is they've just taken those familiar equations of motion and they have substituted in angular movement instead of linear movement. So now angular velocity is what we're talking about, not linear velocity. Angular acceleration is what we're talking about, not linear acceleration. And then the angle is now the position in space that we're talking about, not a linear position. So all of those things have been flipped. And if you look at the equations of motion now, you can compare the linear to the rotational. So here we were talking about velocity. Here we're talking about, remember, this is omega, and this is our angular velocity. Here we're talking about average acceleration. Now we're talking about average angular acceleration. Time is the same. And so you'll notice that all of these that change just change from a linear movement traveling across to an angular movement we're spinning. All right. But all of the equations of motions are the same. So let's look at what that does in a equation. An electric motor normally runs at 1,865 RPMs, right? Rotations per minute. Those are not radians. Assuming a uniform angular acceleration of 64 radians per second squared, what angle will it rotate through to get to the full speed? The full speed. So now we're going to look at like the change in time equation. All right, so that third equation of motion where we have an ending velocity, an initial velocity, and an average angular acceleration there, we're going to plug that in. So we're going to use the formula that's right there in the middle. We're going to say, well, if we want to find the angle that it rotates through, that is the change in the angle, right? And in order to do that, we need to know the ending angular velocity, so to speak. We subtract the beginning angular velocity, and we divide by the average angular acceleration. All right? So that's what we're doing. So it says from a stopped position. That tells us what? It tells us initially that it was not moving. So stopped condition is going to be your initial omega. The normal running, well, that's where we get it to. So this is going to be our ending, so to speak, omega, our final, right? So we have an initial and a final. And then we have an average acceleration, This is what we were used to, except now for all of those linears, for all of those velocities and accelerations, we're plugging in angular velocity, angular acceleration, right? But it's basically the same. So we're just going to plug it in. We're going to say, well, we're going to take that 1865, and that is my ending. However, is that an angle? What is that? That is rotations per minute, correct? What is my final acceleration going to be in? Radians per second squared, right? So I cannot divide a rotations per minute by a radians per second squared. We are going apples to oranges here. So before I do anything, I need to take this rotations per minute and I need to convert it to radians per second, which means every rotation is one circle. In radians, that is what? 2 pi. I am in minutes. I need to be in seconds. So this is what my conversion looks like. I am going to go from rotations to radians, and I'm going to go from minutes to seconds. So in 3 significant digits, we'll use 3 for right now. We'll move on and we'll get it into the 2 when we get down there. How am I moving as far as my radians per second? I actually left it in decimal form for this. I took it all the way out. So I actually went ahead and left the 0.3 right now. If I were stopping here, I would worry about my significant digits. I'm just trying to get as close to the answer as possible before I do my adjustments, right? So you can note that, hey, we're doing 2 significant digits to the end, but at this point we'll wait. So that's actually my ending, all right? That's what I need to use before I plug it into this guy, all right? I've got to get it in the same units of measure or we're gonna have a big problem. Now we're ready just to plug it in. My ending, well, I put that's 195.3, square it. My beginning, I'm from stopping. What is that? 0. Obviously you don't have to write it, but I am for teaching's sake. 2 times my average angular acceleration. They told me that. What is it? Yeah, it is my 64 that they gave me, right? And then I'm going to calculate my radians here. Just a quick reminder, calculators like order of operations, as does the whole world, right? So in your calculator, you can do 195.3 and then do your little squared button. When you divide, you have to do parentheses, 2 times 64 here. Right? So in significant digits, so if I were to do this, 298 radians, if I did only 2 significant digits here, what would that look like? 300, and I need to note that that is 2 significant digits. How would I note it? Underline that second one. Underline that second one. Yep, that is 2 significant digits there. All right, let's look at rotational dynamics. This is where we get into torque a little bit. So we start thinking about the effect of like pivot points on something. Obviously, the seesaw is balanced, which means gravity pulls each side equally. If you've ever sat on a seesaw, you know that it doesn't always stay balanced. In fact, it typically doesn't. That's the whole point of a seesaw, right? But in this case, our seesaw is balanced. That means it is directly perpendicular to the pivot point. By pivot point, I mean the little guy that it's sitting on. In this case, it's in the center. We'll look at ones that aren't. And then you have a distance away from that center. You have the force that's pulling down on it. But at this point, everything is balanced, which is what causes it to look like that, right? Rotational dynamics, what happens is angular acceleration is going to be proportional to the applied force. So if I put force at the end of it, it's going to move. Assuming that we put double the amount of force, it's going to move probably more quickly, right? However, it does not move directly down, right? Feels like it when you're on it, but it is actually rotating, right? This is a rotational movement that is happening. That seesaw is not going straight down like an elevator. It is tilting, right? And it is moving at an angular rate. And so this is what we're going to start looking at is that proportionality that happens to the angular acceleration and how much force you have put at some point that is pivoting at an angle. So the angular acceleration is proportional to the force's position vector. Position vector. It matters how far away from that pivot point it is, all right? So you can see that as this is further away, it's different than here because of where that force is located. Where that force is located compared to the angle. This makes a lot of sense when you start introducing the term torque, all right? The product of the applied force and its position vector. Lots of words, but torque is basically what makes something move angularly. It's like the applied force of angular movement, all right? You think of it as a vehicle, right? When you think of a vehicle, you think of torque. In that world, the torque of a vehicle is going to be how quickly or how much force is being put to cause a quick acceleration in an angular movement, right? We also recognize it when we use tools, and we're going to actually show the pivot point based on that. But if you've ever used a tool, it depends on how long a wrench is versus how much you're going to have. If you've ever seen the ones they use to change tires, you'll notice they're rather large, right? Because they can get more force going on it versus if they had this little tiny tool trying to crank it, all right? And so it matters. And all of that comes into play because of that applied force. So let's talk about all these terms. We have new formulas that are being introduced. They have to do with the angle at which it is located from that center or that pivot. The magnitude of a torque can be calculated by the formula. This is a new Greek letter. Y'all are going to know the whole alphabet before this year's over. This is the Greek letter tau. As you can probably guess, it's similar to our T location in the alphabet, tau. It is R times F times the sine of theta. So what are all these variables? R is the distance from the center of rotation. That's what R typically means. We think of it as radius, all right? But we are going to now think of it as a distance from the center of rotation to the point at which the force is applied. That is your R. Your F is the magnitude of the applied force. If you are sitting on a seesaw, your weight is your magnitude of the applied force. You are pushing down on the seesaw with all of your weight, all right? Magnitude of the applied force. And theta is the smallest angle between R, that distance, and F when positioned tail to tail. And I'll give you a picture of this. So this tau, as a reminder, you have this formula that is created, and you have what's called a moment arm. A moment arm. The moment arm is the component of the position vector perpendicular to the force. Perpendicular to the force. So if you think about it's like the arm coming off from the pivot point to the force being applied on that seesaw. We're sitting on the seesaw. That moment arm is that little arm that connects you from where you are and applying that force to that pivot point. And so you have your standard Newton meters of units of torque, and you have that moment arm, which is calculated by that R times the sine of theta. And so a few more pulling out of what those represent. This is what I think of torque. I mean, I know car is a normal one too. But here you have, this would be your radius, so how far away you are. This is your tau. This is the perpendicular force here. And then you have this angle that's created. So if I were pushing on this in this direction, the angle that's created from the direction on which I'm pushing and directly out from the arm itself is going to be your theta. So it's all relative to how the pressure is being applied to it versus the angle that's created. Torque has the same role in rotational motion that force has in linear motion. All right? So when you think linear motion, when we thought about, we're pushing the block up and friction is pushing against us, right? That is force that's acting linear versus force that's acting rotational. Angular acceleration then is produced by unbalanced torques, all right? Unbalanced torques versus unbalanced forces, right? And so this is acceleration though. It doesn't mean that if something's spinning that they are unbalanced. It could be spinning at a constant rate, and that still means balanced, right? This is what happens with acceleration. It's just like in a car. You can be driving at 60 miles an hour. That doesn't mean you're not moving if you're not accelerating. It just means you're consistent in your movement, right? Same thing with torque, all right? It does not necessarily mean that it is stopped. It means that it's not accelerating, all right? It's not accelerating. So let's look at this. The sum of the forces equals 0. Well, if the sum of the forces equals 0, that means it's not accelerating. Doesn't mean it's not moving, but for rotational motion, when the sum of the torques is 0, you're going to either be at a constant angular movement or you're not going to be moving at all. Those are your only options. You cannot be slowing down. That would be a negative acceleration. You cannot be speeding up, positive acceleration. You could be stopped, not moving at all. That means it's also balanced, or you could be consistently spinning. That would also be a balanced system, all right? But it does mean you're not speeding up or slowing down if they are balanced. Rotational equilibrium then is the state of a system in which all torques are balanced, resulting in no rotational acceleration. That is equilibrium. Rotational equilibrium. Rotational equilibrium. All right, Tim and Paul want to balance a seesaw on the playground. Tim weighs 257 newtons. Paul weighs 229 newtons. The seesaw is 3.6 meters long of negligible mass. That's important. We're just assuming the seesaw is not in this equation. Assume that the pivot point is in the middle of the seesaw. If Paul sits on one end of the seesaw, where must Tim sit to balance the seesaw? So let's think of our logic first. Who weighs more? Well, Tim weighs more, right? If Tim sat at the end, that's going to drop that seesaw, right? Has anyone ever sat on a seesaw with someone that was significantly bigger or smaller than you, right? You have to adjust if you want to balance, right? All right, and so what they're saying is Tim weighs more. Paul is going to sit all the way at the end of the seesaw, but Tim is going to have to adjust himself, or what's Paul going to do? Paul's going to go up in the air, right? And so that's what they're asking. How close does he need to sit to it? All right. So let's talk about what happens with these. First, we're going to talk about what does it mean to be balanced. So let's look at this logically. They didn't give us an angle, but somewhere in my equation is the sine. So remember, this little towel, this new guy, is going to equal my radius, or how far away I am, times my force, times the sine of that theta. Well, if I'm balanced, my theta looks like this. What is the angle of my theta then if I am balanced? If it looks like this right here. Sine of it is 0, but what is the angle itself compared to this and this? That is a 90-degree angle. If it is balanced to the pivot point, it is forming a 90-degree angle. I have this and my pivot point. That is a 90-degree angle if it's balanced, right? What is the sine of a 90-degree angle? For those of you that have not gone through trig, you can plug it into your calculator. Sine of a 90-degree angle. 1. It is 1. So even if you plug it in, first make sure that you are in degrees if you don't know, but the sine of a 90-degree angle is just 1. So in this particular situation, that little tau, that's what we're looking for, is just R times F. R times F. Well, what do I want? What do I know about what's happening on either side? Well, in order for it to be balanced, this tau that's associated with him and that one has to be equal, right? The force has to be equal, or else we're going to have a problem and one's going to be up. So I know that we'll just use, unfortunately they use T's, but we have a little Tim here, and we have Tim's force, and that should equal Paul and Paul's force, right? Paul's force. They should equal each other. Those forces should equal each other, or else we don't have equilibrium if we're talking about torque, right? Right? The rotational force that's happening here. All right. So we're going to say that this is going to be right here. What do we know and what do we not know? Well, I am solving for how far away Tim sits. So I'm going to solve for Tim's little tau here, which represents how far away he is from there. Okay. So I'm going to divide both sides. His little guy here, Paul's, how far away he is, his force, divided by Tim's force. All right, that's what I'm going to do. I'm just solving for the one that I don't know. I need to know how far away he is sitting. How far away he is sitting. All right, so how far away is Paul sitting? Well, they said he sits at one end. How far is that? If the whole thing is 3.6, how far away is he sitting if he's all the way at one end? 1.8. He's half away, right? The whole thing, so he's 1.8. What is Paul's force? What is Paul's force? 229. How do we know that? Well, they told us. 229 newtons. What is Tim's force? 257. And that will tell us how far away Tim is. How far away should Tim be if we want Tim to balance out Paul? He should be 1.6 meters. Think about this. Is it logical that the heavier person should be closer or farther away? It is logical. If you've ever sat on a seesaw, it's logical to you, right? So the heavier person needs to slide in some so that it balances between the two. And that's how you know how far, right? Or if you're a kid, you just adjust until y'all can both sit still, right? But that's what they're doing. They're actually adjusting what's happening to that seesaw because of that angular movement on it. Locating the pivot point. So on the questions ahead of this, they put the pivot point right in the middle and they said, let's put the people certain places, right? Now what they're saying is, hey, I want to put both of them on the end. I want you to move the pivot point. Does that make sense? So now we're going to say, hey, I actually want them both on the ends of this guy, and I want you to move the center of it so that it balances, all right? So we're still going to be using 90, but now what you have to think about is the overall length, all right? So we know that if I were to take how far away Tim is, we'll say Tim, and add it to how far away Paul is from that pivot, it should equal the entire length of the seesaw. Does that make sense? If they're both sitting at the end, the entire length of the seesaw should be how far away each one is from the pivot. Doesn't matter where the pivot is. So let's say we put the pivot here, all right? And this is Paul, and this is Tim, all right? Still gonna equal the length of the seesaw, right? His distance away plus his distance away, length of the seesaw. All right, so that's the concept we're going to build off of here. All right, so what we want to do is we want to just work on one of them. All right, so we want to say, maybe we want to just work on Tim and we want to say use Tim's, or maybe we want to work on Paul's. So what we're going to do is we're going to set them up in a, let's just solve for one of them. So let's say I want to get Paul by itself. Well, that's just going to be L minus him, right? So wherever we solve for one, we'll then have the other. It's pretty much how we're going to do this, all right? So then from that, we're going to say, well, the sum of them, again, we know that their torque should equal each other. So if I want to use Paul, and I want to say, what is his torque altogether? Well, his torque altogether should be exactly how we used it before. It should be how far away Tim is, Tim's force, and that should be divided by Paul's force. This is what we've done on the other two, right? We've said his torque is his R times force. His torque is his R times force. So we can set them equally to each other, and then we can solve. So all I did was say, here's Paul's torque, and here is Tim's torque, right? And I'm just getting a replacement for him is all I'm doing, all right? I'm just getting a replacement for him, all right?
So an FP.
Right, so force of Paul was going to be the force of Paul.
Yeah.